Okay. Last week we discussed the polar form of a complex number. The polar form means when we have a complex number, right? Right. Under polar form, people, we discussed when we have on the Argand plane, this is the real axis and this is the imaginary axis. When we have a complex number represented by the point P, suppose the complex number is Z, right? The complex number Z I can take in the Cartesian form of in the type x plus iy, where both x and y are real numbers. Now, this is the point on the Argand plane which represents the complex number Z. Here, this is the origin. Now, when I join this origin O and the point P by a straight line, we said by the length of this OP and the angle OP makes with the real axis in anticlockwise using the length from O to P, suppose R, and this angle theta, we said we can express this complex number Z. How? This complex number Z, we can write as R times cos theta plus I sin theta. This is therefore called as the polar form of the complex number. Then in representing this way, the complex number, there are the two properties of a line segment we have used. The first property come in here, it is the length of the line segment from O to this P. The other thing is, people, when we go from O to the point P and put in the arrow like this, the line segment going from O, going away from O up to the point P, the line segment makes an angle theta measured in anticlockwise with the real axis. That angle we said as the argument of the complex number Z. This theta, people, really explains the direction of the line segment OP. In the theta here and here, theta gives the direction of the line segment OP. Then here, in this form of the complex number, really we have used the two properties of a line segment, its length and the direction, to represent the complex number. So therefore, length and direction, whenever we use of a line segment to represent anything, there, people, we have the idea of the vector. Vector also, we know, people, we write the size of the vector is given by the line segment, length of the line segment, and its direction is, of course, given by an arrowhead putting on that. The direction expressed by an arrowhead, but people, in order to give that direction of the arrowhead, again we have to use another thing to explain its direction clearly. That is, people, an angle like this measured. Okay, so that is why here we say on the right hand side of this, the length of the line segment is here, its direction is given by this theta. So therefore, the two properties of a line segment only here we have used on the right hand side to represent the complex number in the polar form. So therefore, we said the polar form of the complex number, it has the vector property. So therefore, there we further said, people, this line segment OP we draw on the same Argand plane in another position with the same length and without change the direction. That means the same line segment we draw in another position in the plane parallel to this OP, and length of OP is same as this length, right? This way. Then, you know, when we consider this OP and suppose this is RQ, this RQ length and OP length being equal. So therefore, this R only, therefore here we have. and this line segment and this line segment being parallel. Therefore, this angle is again theta. Then here, this line segment being equal in length and they are parallel. Therefore, these angles are also equal. Therefore, since for this line, the same R, this is available, the same theta here, still available here and here, then we can logically say, people, by this line segment also, RQ should represent the same complex number Z. Because the two data we need to write in polar form of a line segment still available for this RQ as this. Okay. So the vector also, people, we explain like that now. If the line segment has the same length, and suppose this is a vector A, right? This vector A is represented by this pin, suppose. I can bring this pin parallel to this line segment on the board away like this. And I can bring forward, upwards, downward, wherever the position we keep this pin parallel to this line segment, point in the same direction. People, we can say the same vector is represented. The same property here we can apply. That means, people, when we draw on the Argand plane, this way a parallelogram. You know, opposite sides of parallelogram are equal and they are parallel. Therefore, the direction being the same, length of the line segments being the same. So therefore, the complex number represented by this line segment and this line segment being equal. Right, people? So, and not only that, the complex number represented by this line segments also being equal. Okay. So that is the reason, that is because of the complex number polar form has the vector property that we discussed. Right. And finally, in the last class, the recording you could watch that, we of course explain how to mark negative complex number. That means now if we have a complex number like this, people, Z, in order to get minus Z, there we discussed, to get the minus Z, what we said is the same line segment O to P, we have to draw in the opposite direction starting from O. This way. OP is the line segment, the same length we have to draw in the opposite direction starting from O, this way. These two are equal and the arrowhead is now pointing this way. Then at the end of this line segment we have negative Z complex number. That is how we find the negative complex number on the Argand plane. Right. Today we are supposed to discuss how to mark sum of two complex numbers and difference of two complex numbers on the Argand plane. Okay, right. Now then today we will write the first heading as right down this way. The sum and difference. The sum and difference of two complex numbers. The sum and difference of two complex numbers on the argon plane. On the argon plane. Right. Now, people, suppose we have a complex number Z1 and Z2, the two complex numbers. Then, suppose represented by, these two complex numbers are represented by the points P1 and P2 respectively, like this. Right. This is the point P2, this is the point P1. Then, if I join this origin node to this point P1, you see, then OP1, if we draw this way the arrowhead, OP1 line segment represents the complex number Z1 in polar form. In Cartesian form, people, the point P1 represents the complex number Z1. There's nothing to get confused there, right? Now, when I consider this point P1 has real coordinate and imaginary coordinate. Using that two coordinates, you can write the complex number Z1. And in polar form, people, the line segment OP1 by the length of the line segment OP1 gives the R, the modulus, OP1 line segment here, and this angle within bracket cos theta plus I sin theta together give the polar form of complex number Z1. Right. Now, suppose here OP2, right, is the line segment that represents complex number Z2. This is the imaginary axis, this is the real axis. Right. Now, people, we need to mark the point on the argon plane that represents the complex number Z1 plus Z2. You know, when we add two complex numbers, Z1 and Z2, the result is another complex number. Now, for example, if I consider Z2 plus 3i, Z2, 1 plus 2i. When we add Z1 plus Z2, people, real parts we can add, imaginary parts we can add this way. Since this is another complex number, there should be a unique place for this complex number on the argon plane, because the real coordinate is what, 3, imaginary coordinate is 5. 3, 5 point represents what? This complex number Z1 plus Z2. So now I'm going to find out what is that position. To find out that position, people, this is what I do. I'm going to construct a parallelogram so that OP1 and OP2 as its adjacent sides. OP1 and OP2 as its adjacent sides. I'm going to construct a parallelogram OP1 and OP2 as its adjacent sides like this. OP1 and OP2 are the adjacent sides like this. Okay. Right. Now I have constructed a parallelogram. This way. I take this point as P. Okay. Then O, P1, P, P2 is a parallelogram. Right. Then by this parallelogram, now so far we have three vertices O, P1, P2. Fourth vertex is P. By this fourth vertex, people, we get the sum of the two complex numbers Z1 plus Z2. Understand? We can very easily prove this. If I take this complex number represented by the point P as Z, then we can prove Z is equal to Z1 plus Z2 like this. Since people, this OP1, P2 is a parallelogram, these opposite sides are equal in length. And also they are parallel. When we construct these diagonals like this, okay, this way when we construct diagonals, okay, you know the diagonals bisect each other of a parallelogram. Then this length and this length being equal, this length and this length being separately equal. So if I take this point as people say Q, the complex number represented by the point Q in the Argand plane can be found in two ways by using the ratio theorem. The ratio theorem, when we apply for this Z1 and Z2, this is 1:1 because Q is the midpoint. Here also this is 1:1. The ratio theorem we learned. The ratio theorem gives the complex number at the point Q as using this Z1 and Z2, right? We can write complex number represented by the point Q as people ZQ is equal to 1 times Z2 plus this 1 times Z1 divided by 1 plus 1, 2. That means we know the complex number at the midpoint can be found by adding the complex numbers at the extreme points and dividing by 2. Similarly, people, the same complex number represented by the point Q can be found by using the ratio theorem, right? Using here the complex number and here the complex number. Here the both real and imaginary parts 0. Then complex number is 0 plus I times 0. Therefore, the complex number represented by the origin is 0. Here it is Z. Then the complex number at the point Q can again be found by adding this complex number 0 plus this complex number Z and dividing by 2. Then people, the point Q represents the same complex number. So therefore, this left-hand side being equal, the right-hand side should be equal. So therefore, we can say by this, we get Z2 plus Z1 divided by 2 is equal to 0 plus Z by 2. These two you can cancel down. Z equals Z1 plus Z2. This gives Z1 plus Z2 is equal to Z. That is how simply we find the point which represents the sum of the complex numbers Z1 and Z2. So therefore, people, what is the geometrical way of explaining the way of marking the sum of two complex numbers? Yeah, if the complex numbers are Z1 and Z2, they are of course represented by the points P1 and P2 respectively. Then the sum of that two complex numbers Z1 plus Z2 is represented how? By how, people? We construct the parallelogram such that OP1 and OP2 are its adjacent sides. And taking these two sides are adjacent sides of a parallelogram, the fourth vertex of the parallelogram now P1 and P2. After constructing the parallelogram, by the fourth vertex of the parallelogram, people, we get the two complex numbers, right? Even my Wi-Fi becomes unstable. Don't leave the class, wait, right? Okay, so then we'll write one sentence. Write down like this. Let the complex numbers Z1 and Z2 are represented by the points P1 and P2 respectively in the Argand plane. Then the complex number Z1 plus Z2 is represented by the fourth vertex of the parallelogram with OP1 and OP2 as the adjacent sides. Right? Right. Now draw the diagram, people. Draw this diagram. Right. We construct the parallelogram OP1, P2, so that OP1 and OP2 are its adjacent sides. In P1, P2 means three vertices already we have. Is this P? By the fourth vertex only, Z1 plus Z2 we get. Right? Okay. Construct. Then you can write O P1 P2 is a parallelogram. O P1 P2 is a parallelogram. Okay. Now write down. Let Q be the point of intersection of the diagonals Q be the point of intersection of the diagonals. Now write down, by ratio theorem, we can find the complex number represented by the point Q. represented by the point Q. Represented by the point Q. Right. Find that in two ways, people. And take the answer. Right. Okay, now people will see, we said that this is the parallelogram now. Then this OP2 line segment is equal to in length P1 P line segment. And this OP2 line segment is parallel to P1 P line segment. That we say, you know, OP2 line segment is parallel to P1 P line segment. Then the complex number, you know, represented by the line segment OP2, and the complex number represented by the line segment P1 P should be equal. Right. Then starting from P1 and ending at P, we have a line segment. No? By that line segment on the argon plane, that line segment represents a particular complex number. That complex number should be equal to the complex number represented by OP2 line segment, that is Z2. That means P1 P line segment should represent the complex number Z2. People, now this P1 has the complex number Z1. At the point P1, the complex number Z1. Point P. Then if I take that complex numbers Z1 here is Z. Starting from P2 ending at P1 to ending at P1 P. Line segment people should represent the complex number Z2. This Z means really Z1 plus Z2. No? Then I am going to write that as Z1 plus Z2. Right? This one. Then from P1 up to P, this line segment should represent the same complex number represented by the line segment OP2, that is Z2. Then P1 to P line segment should represent the complex number Z2. Then people, you can very clearly see, when you start from a line segment, right, and ending at a point on the same line segment, by that line segment, the representing complex number can easily be found, people. Here the order of the line segment from P1 to P. Yeah, ending point complex number Z1 plus Z2. From that, subtract starting point complex number. Then you can very clearly see, when you cancel down this and this, we get the complex number. People, this thing, of course, we discussed for vectors also. Right? So we said what? When we have a line segment AB with position vectors simple A and simple B, then A to B, AB vector is equal to, here, second letter position vector simple B minus first letter position vector simple A, B minus A. The same thing is valid here too for the complex numbers. Why? We said what? The complex number has vector properties. Understand? So therefore, whenever you see a line segment on the argon plane, right, the complex number represented by that line segment on the argon plane can easily be found. There are people, the order of moving along the line segment is very important, right? Now, when we move from P1 up to P by the line segment P1P, The complex number represented can be found. Ending point complex number minus starting point complex number is the way of finding the complex number represented by that line segment. That is very similar to finding a vector by using the position vectors at its endpoints. Okay, like this: A to B vector is equal, AB vector equals B minus A. Understand? That's the way. Okay, right. So then we can furthermore notice this one when we do the other one, the difference of the two complex number when you mark. Thereafter, we'll take a brief note. People, these things when you understand clearly, very easily, we can go ahead of this lesson without any problems, right? So these are the theories that you have to very carefully understand. Okay, you can now obviously see that, right? Now we'll see how to mark the difference, Z1 minus Z2. All right. So now write down the next one as to mark Z1 minus Z2. Right, now write down to mark Z1 minus Z2 in Venn diagram. Write down Venn diagram. Okay. People, this Z1 minus Z2 can be, of course, explained as this way. Z1 minus Z2 complex number, I can think like this: Z1 plus minus Z2, like this I can think. We add to the complex number Z1 what? Minus Z2 complex number. We add minus Z2 complex number. Then we get Z1 minus Z2. Then in this case, we can do the construction like this. Suppose here we have, right, this is the real axis, this is the imaginary axis. Suppose the complex number Z1 is this. It is represented by the point P1, right? Complex number Z2, this, it is represented by the point P2, right? Now to get this Z1 minus Z2, that is Z1 plus minus Z2. Then to the Z1 complex number, we have to add minus Z2. Minus Z2 complex number can easily be found right. Now we noticed that when we are given a complex number Z, how to mark minus Z? People can remember that one. When we have a complex number Z like this, to mark the minus Z, we said what? This line segment we have to produce in the opposite direction starting from origin like this, so that this and this being equal, then this end we have minus Z, right? Then here also, in order to get minus Z2, what I need to do is, people, the line segment is OP2, I have to draw starting from this O in the opposite direction like this. See, right? This and this being equal. Then at the end point of that, we have, people, this way minus Z2 complex number. Right? I'll take this as, people, P3. This is minus Z2. Right? The arrowhead is going this way. Right. Now, people, we need to add this Z1 and minus Z2. Then the line segment that represents the complex number Z1 is this OP1. Minus Z2 is represented by this OP3. Then to add that Z1 and minus Z2, we have to construct the parallelogram OP1 and OP3 as its adjacent sides according to the previous proof we need. We earlier in the previous case, people, we added two complex numbers. No. One is the complex number Z1, other one is Z2 this way. To add this Z1 and Z2, we had to construct the parallelogram with these two line segments as its adjacent side. Then by the fourth vertex, we get Z1 plus Z2. Like that, to add what this Z1 and minus Z2, now what we need to do is, people, OP1 and OP3 line segments as the adjacent sides of a parallelogram, we have to construct the parallelogram. Then its fourth vertex, already we have three vertices, no, people, O, P1 and P3. The fourth vertex will give the sum of the two complex numbers Z1 and minus Z2. Z1 plus minus Z2 means, people, Z1 minus Z2. Understand? So therefore, when we construct the parallelogram now with this OP1 and OP3 as the adjacent sides, this is what we get. Right? This then this must be parallel, no? Like this. Right? So then here at this point P, that should be given Z1 minus Z2. Then the corresponding line segment which represents the complex number Z1 minus Z2 is this OP. Okay. Okay. So now this O, P1, P, P3 is a parallelogram. So therefore, this length and this length being equal. And this OP2 and OP3 lengths also being equal, people. Why? Here this is Z2, this is minus Z2. Right. Okay. All right. So then we can start it like this. Write down. Z1 minus Z2 is equal to Z1 plus minus Z2. Right. Now we construct minus Z2 and come to this. Right now, yeah. Right, people, now. Okay. I will write one sentence like this. First construct this one and we'll write one sentence. Let the point P3 represents the complex number minus Z2. Minus Z2. Now construct the parallelogram. Now construct the parallelogram. Construct the parallelogram. O P1 P P3. O P1 P P3. O P1 P P3. Now construct the parallelogram O P1 P P3. Then people, that says we construct the parallelogram with OP1 and OP3 are as the adjacent sides. Okay, that automatically included in that. Then write down. Then the point P represents the complex number Z1 minus Z2. The complex number Z1 minus Z2. Right. And now people, after this, we can see this earlier said property again in this diagram too. What is that? You know, here O P1 P P3 is a parallelogram, no? O P1 P P3 is a parallelogram. So therefore, people, this OP3 and P1P are parallel and equal in length because it's a parallelogram, no? Right. Now, people, when you pay your attention to this four verses O, P, P1, P2, there I join this P2 and P1 like this. Then you can see this OP2 and this PP1 are parallel. Why? You know, OP2 and OP3 are same line, no? Right? Therefore, OP3 and OP2 are parallel, same line, therefore parallel. Don't consider the order of letters I am reading here. OP2 and OP3, same line, they are therefore parallel. Right. And this is what? O, P1, P, P3 parallelogram. So therefore, this and this being parallel. This and this being parallel, this and this being parallel. Therefore, this and this being parallel. That means people, O, P2 and P, P1 are parallel. Not only that, people, the OP2 and PP1 lengths are also the same, equal. Then OP2 is equal to PP1. OP2 is parallel to PP1. Therefore, in this quadrilateral OP, P1, P2, two opposite sides are equal in length and parallel each other. Therefore, people, what can you say about this OP, P1, P2 quadrilateral? It is a parallelogram. Why? In any quadrilateral, if the opposite sides are equal and parallel, that quadrilateral is a parallelogram. So therefore, people, you can see OP line segment and P2, P1 line segments are parallel and equal in length, right? This way. If I take this notation here to denote that, OP and P2P are equal in length and parallel, right? Then we'll write, putting a star mark. In the diagram, O, P, P1, P2, O, P, P1, P2 is a parallelogram. O, P, P1, P2 is a parallelogram. Therefore, OP is equal to P2, P1 and OP is parallel to P2, P1. Correct, no? And now people, these two line segment, OP and P2, P1. See the direction I am moving, O to P, this direction, and P2 to P1, the same direction. Huh? The two line segments are equal in length and they are parallel. Not only that, when we move from O to P direction in both line segments, then according to the vectors, people, this OP vector and P2, P1 vector must be equal. Why? All the qualities or conditions required for two vectors to be equal, they satisfy. Since the complex numbers are very similar to the vectors, now you can very clearly say OP line segment gives the complex number Z1 minus Z2. Therefore, P2P line segment should give the same complex number Z1 minus Z2. Understand? Then you can write, therefore, the line segment P2P1 should represent the complex number Z1 minus Z2. Z1 minus Z2. Z1 minus Z2. People, now you can again verify that earlier the result I told you. When you start from P2 and ending at P1, then by the line segment P2, P1, the complex number we get is what, people? Ending point complex number minus starting point complex number. Correct, no? We start from P2 ending at P1, no? P2, P1 is equal to Z1 minus Z2. That is very similar to writing a given vector using the position vectors at its ends. Understand? Very similar, people. That should be so. Why? Because complex numbers, the polar representation really containing the vector ideas. Okay. So then you can then write here P2, P1 gives Z1 minus Z2. Then under that you can write complex number at P1 minus complex number at P2 is the way of writing the complex number represented by a line segment. Understand, people? Right? Yeah. Then again we can write this down as another note to emphasize this again. Right now, come to a note like this. Write down let the points Q in room the complex numbers represent the complex numbers and respectively. Like this. Suppose like this. Point here, suppose P, here suppose Q. Point P gives is at P, point Q gives is at Q. Right, like this. Then first thing is this. First thing is, people, the line segment PQ represent the line segment PQ represents the complex number. What people? PQ use complex number at Q people. Is it Q minus is it P? Number 2. Number 2. The line segment QP. The line segment QP represent the complex number. QP represent people complex number at P is at P minus is at Q. There, remember the order of moving along the line P to Q and Q to P being people very important. If you match this with vectors people, that's the way to remember this very easily. Nothing different between complex number polar form and vectors, they are the same idea. The way you keep in your memory the vector properties, the same way you can remember this property also, because they are the same, right? Right, people. Now, after this lesson, as I told you people, there are more theories in it. There are more theories. Without knowing these theories well, people, we can't work out questions. Okay, so therefore, we have to do some more theories. After finishing the theories, we'll discuss questions. Then you will find this lesson is very easy one. But people, in your memory, the theories you have to have in a good condition. In the sense, in the good condition mean people, right? At once you get something, you should be able to remind that one and clearly understand that. Then only people you can suddenly at once catch what the question. Then only you can answer that. Once I explain the way of getting the answer, you can very easily understand that one if you have these theories in your mind. Yeah. People, now the next one we are going to discuss is this. We are going to multiply two complex numbers and we divide two complex numbers in polar form, right? Thereafter, we'll see some more theories available in that too, right? So then we'll write the next heading as this way. Next heading. Multiplication and division, write down multiplication and division of two complex numbers in polar form. In polar form. Right. People now will write like this in polar form. Let Z1 R1 times cos theta 1 plus I sin theta 1 and Z2 R2 times cos theta 2 plus I sin theta 2. Okay. I sin theta 2. Right. Then people you can very clearly see then Z1 modulus is what people? R1, no? And what is the argument of Z1? Arg Z1? This theta 1. Then mod Z2? It's R2. Arg Z2 is people theta 2. This we have. Right. Now let's see what is this Z1, Z2 product in polar form. Right. Then people, we are going to multiply this Z1 and Z2. This is Z1 and Z2 I am going to multiply. What is Z1? R1 times cos theta 1 plus I sin theta 1 into Z2 R2 times cos theta 2 plus I sin theta 2. Now I can multiply this R1 and R2 means people two positive real numbers. No? We can multiply them. Right. R1, R2 like this I can write. Then I am going to multiply by cos theta 1 and this cos theta 2. Cos theta 1 into cos theta 2. And this I can multiply. I and I squared, it is minus 1 sin theta 1 sin theta 2. Right. And people, the next one is by this I sin theta 1, we have to multiply this. By this cos theta 1, I have to multiply this. Then you know I is coming from them. Then I can take this I out. Then sin theta 1 into cos theta 2 plus cos theta 1 into sin theta 2. This way we get. Right, people? It is sin A plus B. Sin A plus B. Then we Z1 Z2 is equal to R1 R2. Within bracket we can write cos theta. This is what we get for what Z1 Z2 product. Z1 Z2 product. People, by the right hand side, can you tell me what is the argument of this Z1 Z2 product? Is this theta 1 plus theta 2? What is the modulus of Z1 Z2 product? R1 R2, product of the modulus of the complex numbers. By this we get what? By this simply we get Z1 Z2 modulus. In the left hand side complex number, its modulus available here, no people? R1 R2. But what is people R1 separated when we consider? It is the mod of Z1 into R2 is people mod of Z2. Okay. Part B. Argument of Z1 Z2 product. It is here theta 1 plus theta 2. What is people theta 1? Arg Z1, theta 2, arg Z2. Arg Z1 plus arg Z2. People, by the second result, what do you get? That's the most important one. When you multiply two complex numbers, what happened to the argument of the product? Argument of the product. Product means people after multiplying the two complex numbers, the answer. Z1, Z2, we multiply. Then we get an answer. Its argument is this. This relation says that argument of the product is equal to sum of the arguments of the complex numbers. Sum of the arguments of the complex numbers. Right? We multiply two complex numbers and we take its argument. Right? The argument of the final answer is equal to sum of the arguments of the complex numbers. Sum of the arguments of the complex numbers. This is very important result. Okay, so that means when we consider this way, people, three complex numbers we have in the product. When we multiply this Z1, Z2, Z3, three complex numbers together and getting finally one answer, it's now complex number. If we try to find its argument, that argument, people, is equal to sum of the arguments of Z1, Z2, and Z3. Understand? Why? We can prove this by just using what? Induction. We can write this Z1 and Z2. That product will give one complex number, no people. If I use Z1, Z2 product, when you assume as single complex number Z, now really within bracket, what do we have? Z and Z3. Then here we have only two complex numbers in the product. For that, you can apply this result. Okay. Then I can write this is equal to arg Z plus arg Z3. But now this Z is what people? Z1, Z2. Z1, Z2. Arg Z3. Now here, product of two complex numbers available. Then its argument, again, we can write by using this result. What is that, people? Arg Z1 plus arg Z2. And then this is arg Z3. See here, the result we get like that. Then by using the actually induction, we can write whatever the number of complex numbers in the product we have. Final product is a complex number. its argument can easily be found, people, by adding the arguments of the complex numbers available in the product. Understand? So therefore, remember this result. This is, of course, another important result we use whenever we work out questions, and we use this in other theory to prove that theory. Right. So then we'll write, people, here not. Right. Here we can write this as a not. Come to this one as the not. Arg Z1, Z2, Z3. And take this result. Now, people, we'll come to the next one. Division. We are going to consider division. Z1 complex number we divide by Z2 complex number. Right. Come to division. This is a multiplication. Now we come to the division. Take Z1 divided by Z2. Z1 divided by Z2, the division. Z1 is, people, R1 cos theta 1 plus I sin theta 1. Z2 R2 cos theta 2 plus I sin theta 2. Like this. Now, whenever we have a division, people, to convert this to a complex number, the usual method is, people, by multiplying numerator and denominator by the conjugate of the denominator. Right. So then here Z1 divided by Z2. These two are positive real numbers. I keep like this, R1 by R2. And this is written as cos theta 1 plus I sin theta 1 divided by cos theta 2 plus I sin theta 2. Into both the numerator and denominator we multiply by the conjugate of the denominator. Cos theta 2 minus I sin theta 2. And this one also cos theta 2 minus I sin theta 2. Now multiply these people, multiply these two, and try to simplify this. Right, people. Now see what you get there. Z1 divided by Z2. R1 divided by R2. Right. The denominator is like A plus B into A minus B. Then we can write that as A squared minus B squared. Square of this minus square of this. Cos squared theta 2 minus I squared sin squared theta 2. Now here, this and this we can multiply. Cos theta 1, cos theta 2. This and this you can multiply. I and I squared, it's minus 1. And this minus 1 is plus. Sin theta 1, sin theta 2. Right. Plus. Now, This and this we multiply, this and this we multiply. There we have I. Right. Sine theta 1, cos theta 2, this and this, and minus cos theta 1, sine theta 2. Like this. Even now you can see here Z1 divided by Z2 equals R1 by R2. Right. Now, what is this? Cos A, cos B plus sin A, sin B. What is that? Cos A minus B form, no? Right. Cos theta 1 minus theta 2 plus I sin. Here, what is this? Sin A cos B minus cos A sin B. Here, sin A minus B. Sin theta 1 minus theta 2. Divided by, here people, I square this minus 1. That minus and this minus make plus. Then here we have cos square theta 2 plus sin square theta 2. It is 1, no? This is 1. Right. So then what we get is, this is within a bracket now we have. Then we have people, I can write that we are here. Cos theta 1 minus theta 2 plus I sin theta 1 minus theta 2. Then this is what we get for Z1 divided by Z2. Right now. Right now, by this, see what are the results we get. A. Z1 divided by Z2. Its modulus. The left-hand side people, Z1 divided by Z2 is a complex number because we at the very beginning we proved what when we divide any two complex numbers, the result is another complex number. No? So therefore, this Z1 divided by Z2 is a complex number. Then its polar form only on the right-hand side we have. In the polar form, the first figure we have before the bracket is people, the modulus of the left-hand side complex number. It is therefore Z1 divided by Z2 modulus is now people R1 divided by R2. R1 is nothing but mod Z1. R2 is mod Z2. This is the first one. This result we know already, people know. We proved this one. No? Z1 divided by Z2 modulus is equal to mod Z1 divided by mod Z2. We proved that. Right. Now, part B. Argument. Arg. Z1 divided by Z2. It is on the right hand side here, theta 1 minus theta 2. Here people, though you use the simple A is the very common one to write here. We know the capital A we use for the principal argument, no? But that is not that much an issue, people, right? Right, so simple A whenever you use here, instead of this capital A, never mind. Or everywhere when we use simple A, that's also okay. Right. Now, what is this really? Theta 1 arg Z1. Right? Or just we can write like this. And arg Z2. Arg Z1 divided by Z2. What is this result? This is the one bit important because this is we know previously. When you divide two complex numbers, people, what happened to the argument of the resulting complex number? The argument of the resulting complex number is, people, difference of the arguments of the complex numbers What is the order of the taking the difference of the arguments? Numerator complex number argument minus denominator complex number argument. Numerator argument minus denominator argument is the way of getting the difference of the arguments, right? So this is the next result. They are very important, right? Right. Not only that, people, we should know this Z1 and Z2 are two complex numbers, no? Then Z1, Z2 product also another complex number. Then that complex number also available where? In the Argand plane. Then we should be able to identify the exact location of Z1, Z2 product complex number on the Argand plane. Now we are going to find out how to mark Z1, Z2 product. How to identify the location of Z1, Z2 product. Right? Right. Okay. Then we write next subheading like this, people. We write a subheading like this. To mark Z1, Z2 and Z1 divided by Z2 in Argand plane. In Argand plane or Argand diagram. Right, now I'm going to first mark this Z1, Z2 product. First on product. Z1, Z2. Right, now people, Z1 is this, Z2 is this. This is how we mark it. Now you can very clearly understand, we of course just now found the Z1, Z2 complex number is equal to R1, R2 cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. No? Then whenever we represent this Z1, Z2 product in the Argand plane, the line segment which represents this Z1, Z2 product should have the two properties. The length of the line segment should be R1, R2 product, and that line segment should make an angle theta 1 plus theta 2 with the real axis in anticlockwise. If we can find such line segment, then that is the required line segment which represents the product Z1, Z2. I think you can understand. Okay, yeah. So now what I'm trying to tell you is, people, I should find a line segment whose length is R1, R2, because the argument of Z1, Z2 is R1, R2 product, and this angle should be theta 1 plus theta 2, because the argument is theta 1 plus theta 2, like this. Okay, then by the ending point, this represents this is the point that represents the Z1, Z2 product. And in the polar form, we know in the polar form the complex number can be represented by a line segment. No? Then to represent this Z1, Z2 product complex number, the corresponding line segment is going to be this. Okay, then this line segment only we need to find, right? Then people, this is how we find that line segment. Very carefully listen to this. Right, now I'm going to first mark on the Argand plane the complex number. This is the real axis, imaginary axis, origin no. I am marking here, people, the complex number Z1, suppose represented by the point P1. Then this length is R1. This angle is θ1 because complex number Z1 has the modulus R1 and argument θ1. Right. So now I am going to mark Z2 complex number like this. It is given by P2. Z2. The corresponding line segment should be having the length R2 and this angle should be θ2. This angle should be θ2. Because the argument of the complex number Z2 is θ2. That's the reason. Right. Now up to here you can very clearly understand. Right. Now people, what we do is this. On the real axis, we select a point Q so that OQ length is 1. Okay. And now I am going to construct this OP1Q triangle like this. I take on the real axis a point Q so that OQ length is 1 unit. Now I am constructing OP1Q triangle. Okay. Yeah. Now I am going to take this angle as people beta. Right. Now I am going to draw another line above the line OP2. Above the line OP2, I am going to draw another line above the line OP2, starting from O, making an angle θ1 with this OP2. I repeat that again. I am going to draw a line that starts from O, going above this OP2, making an angle θ1 with OP2 like this. Right. So this angle is now θ1. So that this new line I drew makes an angle θ2 plus θ1 with the real axis. Then the argument, of course, we have now provided. Of what? Of Z1, Z2. Its argument going to be θ1 plus θ2? No. So then that angle available up to here θ2, here θ1, then argument is θ1 plus θ2. So then that point which represents Z1, Z2 product, right, should be somewhere on this line. Because this is a line which makes the argument θ1 plus θ2 with the real axis, right? Now people, in order to find exactly on this line that point which represents the complex number Z1, Z2 product, secondly what we do is this, right? This angle beta, no? People, starting from the point P2, we draw a line so that O P2 P. I draw a line from this P2, right? That line cuts this, the line we just now drew at a point P, so that O P2, this angle becomes beta equal to this. See here, I draw here, right, people? I draw here a line this way. This angle is beta. This is P. Okay. Now see, right? This point is P. Then the point P gives the product Z1, Z2. How to prove that? Proof can be done like this. I'm going to take people this length as R. Then we can see, when you pay your attention to triangles O P1 Q and O P2 P. When you take that two triangles, this angle beta is equal to this beta. This is θ1 equal to this θ1. Then obviously this angle and this angle must be equal. Therefore, these triangles O, P1Q and O, P2P are people what? Similar triangles. Similar triangles. Or equiangular triangles. You know, for two similar triangles, so equiangular triangles, one relation we can write. What is relation? Ratio of the corresponding sides of the triangles are equal. Then for these two triangles, people, you can write OP and OP1 are the corresponding sides. When you divide them, should be equal to people OP2 divided by OQ. OP1 is R1, OP2 is R2, OQ is 1. Use this way, cross multiplication. Then we get R1, R2. Then this length going to be what, people? R1, R2. Now correct me. What line segment represents the product Z1, Z2, people? The line segment which has the length simple R1, R2 product with making an angle θ1 plus θ2 with real axis in anticlockwise. Both property now belongs to what? This line segment OP. The length from here to here OP just now we found R1, R2 product. And that line segment OP makes here θ2 plus θ1, whole angle θ1 plus θ2. Then definitely the point P should represent the complex number Z1, Z2 product. And the polar form, the line segment OP gives that Z1, Z2 product. That is how, people, we find the point on the Argand plane which represents the Z1, Z2 product. Is it clear, people? Right. Then first construct this diagram and we'll write that in words. Right. Start, people. Start this. Draw this diagram and we'll write one sentence. Right. First draw the diagram. Okay, people, then we'll take down few sentences regarding to find the point P which represents Z1, Z2. Write down like this. Let the points P1 and P2, let the points P1 and P2 represent the complex numbers Z1 and Z2 respectively. Z1 and Z2 respectively. Write down. Let capital Q be a point on the real axis such that OQ equals 1. Write down. Let OQ P1 angle, OQ P1 angle equals beta. OQ P1 angle equals beta. Right, now write down, people, like this. Now draw a line from O which goes above OP2, which goes above OP2 making an angle theta 1, making an angle theta 1 with OP2 and choose a point on this line, choose a point P on this line, choose a point P on this line such that OP2P angle equals beta. OP2P angle equals beta. Now, the point P represents Z1, Z2 product. Z1, Z2 product. Right. Asking a question, should always this OQ be 1? Yes. We select a point Q on the real axis, Q, so that OQ length is 1. Otherwise, according to this one, this OP length never be R1, R2 product. Okay. Right. Now, write down like this. Write down like this. By the diagram, OP1Q triangle and by the diagram OP1Q triangle and OPP2 triangle, OP1Q triangle and OPP2 triangle are similar triangles. Within bracket, write down people, equiangular triangles. The same thing, huh? Equiangular triangles. You can write now, people. Then write down OP divided by OP1 equals OP2 divided by OQ. OP1 is people R. We have taken that as R. R divided by R1 equals R2 by 1. Then we get R equals R1, R2. And by the diagram, obviously, you can say people, OP line makes an angle theta 2 plus theta 1. So therefore, the both properties required to represent the product Z1, Z2, the line OP satisfies. The angle Z1 plus Z2, length R1, R2. So therefore, line segment OP represents the complex number Z1, Z2. This is how we just prove it. Right. Then you can write last sentence. OP equals R1, R2, and it makes an angle theta 1 plus theta 2 with positive real axis in anticlockwise sense. With positive real axis in anticlockwise sense. Therefore, point P represents the complex number Z1, Z2. Right now, people? Yeah. Now, second one, division. Take people the second one as a division. Second one, take division. Take second one, division. Z1 by Z2. Okay. Let's see how to find the point which represents the division Z1 by Z2. Right? Yeah. Now this is the imaginary axis. This is the real axis. Right. Now first we mark people Z2 with lesser argument. Theta 2. Like this, huh? Right? This way. Suppose P1 is the point. Complex number Z1. Here O, this is theta 1. R1. No, theta 2. Denominator only we mark first. Z2. It's R2. Theta 2. We mark people the denominator first, like this. Remember this construction, right? Now we mark like this. P2 here. P1 here. Complex number Z1. This length R1. This angle theta 1 people. Right? You know, people, the complex number that represents Z1 by Z2 should have the length R1 by R2 and the angle theta 1 minus theta 2 with the positive real axis in anticlockwise. Right. Now, this is how people we find that point. As before, we select the point Q on the real axis so that OQ length is 1. Then I construct this triangle. Now this angle we select as beta. Right. Now what we do is, people, we draw a line through O. Below this OP1 that makes an theta 2 with this OP1. We draw a line through O, but below this OP1. Like this, below this OP1, so that the angle it makes with this OP1 as theta 2. This is theta 2. Then you can very clearly see here, from here to here, here to here theta 1. This is theta 2. Then from here to here it is theta 1 minus theta 2. That is the required argument of the line segment which can represent the complex number Z1 by Z2. Okay, so therefore somewhere on this line, that point which represents Z1 divided by Z2 must be available. Right. Now we select a point on this line. Suppose that point is P, so that O P1 P, this angle will be equal to this beta. Now then select here like this. A point P select here, so that this angle is beta. Then here, this is theta 2, this is theta 2. This is beta, this is beta. Then definitely this angle and this angle being equal, right? That is, you can very clearly understand that one. Then people, that point P represents Z1 divided by Z2 complex number. This is how we find the point which represents division of two complex numbers. Understand? Right? Right. Now this is the construction. Right. Then we first draw the diagram and we'll write in one sentence the way of finding the point P. Right. Right, people. Start. Right. Here shall we write then the knot? Write down like this. Let the points P1 and P2, let the points P1 and P2 represent the complex numbers Z1 and Z2 respectively, as shown in the diagram. Now choose a point Q. Now choose a point Q on real axis so that OQ equals 1. OQ equals 1. Let OP2Q angle equals beta. OP2Q angle equals beta. Now draw a line from O that goes below the line OP1, below the line OP1, making an angle theta 2, making an angle theta 2 with OP1 . and choose a point on this line. Choose a point P. Choose a point P on this line such that OP1 P angle, OP1 P angle equals beta. OP1 P angles equals beta. Angle equals beta. Then the point P represents. Then the point P represents the complex number Z1 divided by Z2. Z1 divided by Z2. Right. We can roughly prove this proof, people. If I take this length as R, now you can write by the diagram OP2Q triangle and OP1P triangle are equiangular triangles, equiangular triangles, or similar triangles. Therefore, OP1 divided by OP2 equals OP divided by OQ. OP1, people, you know R1, OP2 is R2, OP is R, OQ is 1. Then this gives us what, people? R equals R1 by R2. Correct, no? The required length of the line segment which represents Z1 by Z2 should be R1 by R2. That comes. Now also, people, this angle to this OP from the positive real axis in anticlockwise is going to be this whole thing θ1, this is θ2, therefore θ1 minus θ2. Right? So then we get the complex number by point P. Right. Now you can write OP equals R1 by R2 and it makes an angle θ1 minus θ2. This angle, people, huh? θ1 minus θ2 with positive real axis in anticlockwise. Therefore, point P should represent the complex number Z1 by Z2. Z1 by Z2. Okay, people? We'll move to next theory. Rotation of a complex number about a point in the Argand plane, right? This is, of course, known as a rotation theory, right? So let's see what is this theory. Write down the heading as a rotation of a complex number. Rotation of a complex number rotation of a complex number about a point rotation of a complex number about a point in the Argand plane. In the Argand plane, right. Right, people, now suppose we have this is our Argand plane, right? I guess this heading. This is our Argand plane. Symmetry axis. This is the real axis. This is the origin, no. Right. Now, suppose people we have a complex number is a naught. Is a complex number is a naught. It is represented by the point P naught. Right. And here, suppose we have a complex number Z1 represented by point P1. Right. Now, when I join this P naught and P1 this way, the line segment from P naught to P1, when you put the arrow like this, line segment from P naught to P1, right, people? What is the complex number P naught P1 line segment represents? Ending point complex number minus starting point complex number, right? P naught P1 line segment represents the complex number Z1 minus Z0, right? So now this P naught P1 complex number, right, that line segment now rotated in anticlockwise by an angle theta, and then that P naught P1 line segment comes to a new position like this, right? Then people, this same P naught P1, this line only rotated to this position. Then you can very clearly understand this P naught P1 length m. This point I am going to take as people P2, right? By the point P2, it is another point on the Argand plane of people. So therefore, any point on the Argand plane represents a complex number. Then this point P2 should also represent a particular complex number. I am going to take that as Z2. This is Z2. Now I am going to find out this Z2 complex number. Okay. So then this way I am going to draw the arrow on the P naught P2, this direction, right? So then I am producing this line now this way, right? This way. Right. I'm going to take people this angle as theta 1 and this angle theta 2. Theta 2. Right. Okay. Right. Now we'll write people. First, people draw this diagram and then we'll write one sentence. Draw the diagram there. Right now, we'll write people like this. Write down. Let the points P0 and P1 represent the complex numbers Z0 and Z1 respectively on the Argand diagram or in the Argand diagram. Let the line segment P0 P1 is rotated about the point P0 by an angle theta in anticlockwise sense. Let the new position of the line BEB P0 P2 representing the complex number Z2 by the point P2 right, by the point P2. Okay. Now, people, you can very clearly understand the P0 P1 line segment only coming on to this position. Then P0 P2 length and P0 P1 length being equal. Right, that is well obvious thing. P0 P1 length is equal to P0 P2 length. That is well obvious thing, no? Like this pen is rotated from this position to another position. The lengths being equal. That is well obvious thing, no? Right. Next part, right? Now you can see very clearly, people, the P0 P1 line segment represent P0 P1 gives the complex number. What, people? P0 P1 P naught P1 gives the complex number Z1 minus naught, right? Then you can write, and then you can write people P naught P1 length. What is this? P naught P1 length mean the line segment P naught P1 gives the complex number Z1 minus Z0. Then when a line segment represents a complex number, then the length of that line segment is people equal to modulus of that complex number. Correct now, people? You know, when we consider on the Argand plane, this is the complex number Z. This is theta, right? So then this length, we said what? Is the modulus of Z. Okay. Then the P naught P1 line segment represent the complex number Z1 minus Z0. Then P naught P1 length should be equal to the modulus of the complex number represented by that line segment. It is modulus Z1 minus Z0. And also, people, argument you can write arg of Z1 minus Z0. What is the argument? P naught P1, arrow is going away. Once you bring this P naught P1 line segment to the origin O, going away from the origin O, then this angle theta 1 will be traced here, giving argument of P naught P1 complex number Z1 minus Z0 complex number is people theta 1 by the diagram. Right. Similarly, you can write. Right? P naught P2 gives the complex number Z2 minus Z0. Then P naught P2 is equal to modulus of Z2 minus Z0. And argument of this Z2 minus Z0 is people is theta 2. Theta 2. Right. Now you can write, since P naught P1 is equal to P naught P2, we can write people dividing P naught P2 by P naught P1. This is 1. P naught P2 mean this Z2 minus Z0 modulus. P naught P1 Z1 minus Z0 modulus is equal to 1. People, can you remember, we proved last week, when we divide Z1 by Z2 and when you take the modulus, this is equal to modulus of Z1 divided by modulus of Z2. This kind of result we proved. Using its converse, people, this complex number modulus divided by this complex number modulus, I can write in modulus once like this and write it inside that this way, Z2 minus Z0 divided by Z1 minus Z0. This is 1. This is okay, right? Now, secondly, people, second thing, you can write this by the diagram. You can write this theta 1. People, when this is theta, this is also theta. Theta 1 plus theta is equal to theta 2. Theta 1 plus theta is equal to theta 2. Then theta can be subjected taking this right hand side, theta 2 minus theta 1. Then theta equals theta 2. Theta 2 is, people, arg z2 minus z0. Theta 1 arg z1 minus z0. Right. Now, today we proved something like this. When we divide two complex numbers and when we find its argument, this result is equal to what, people? Arg of numerator minus arg of denominator. Right now. Then here also, this z2 minus z0 is a complex number. At the very beginning of the lesson, we said what difference of two complex numbers is another complex number. No? Then this is a complex number. Its argument here we have. Minus this is another complex number. Its argument here we have. Then really on the right hand side, what we have? The difference of arguments of two complex numbers. It is very similar to say this. This kind of difference of arguments of two complex numbers, we can write as in the left hand side. How? Writing arg1s and writing at the numerator the right hand side first complex number, and then denominator right hand side second complex number. Then, people, this one I can write by using the left hand side of that result like this. Theta equals arg z2 minus z0 divided by z1 minus z0. Right. Now we have the two relations like this. Right. People, you know, when we write a complex number in polar form, when we write a complex number in polar form, right? When you write a complex number in polar form, people, what we really need is z equals r times cos theta plus I sin theta, no? The polar form. Then what is this r? R is the left hand side complex number modulus. What is this theta, people? Arg is it. Then if we know modulus of a complex number and its argument both, if we know modulus of a complex number and its argument both, if we know, then, people, using that modulus and argument, we can write the complex number in polar form in the form r times cos theta plus I sin theta. Then here, look at this. Within this modulus sign, what is the complex number we have? Z2 minus Z0 divided by Z1 minus Z0. This is the complex number now we have in hand. What is the complex number? Z2 minus Z0 divided by Z1 minus Z0 is the complex number. Its modulus is 1. The same complex number only, people, here we have here. Z2 minus Z0 divided by Z1 minus Z0. Its argument only here we have as theta. Then our in-hand complex number is, people, this. Its modulus we know and its argument we know. That means of a particular complex number, its modulus and argument both we know. Then, people, that complex number we can write by using polar form. What is the form? This. Therefore, people, now this complex number, Z2 minus Z0 divided by Z1 minus Z0 complex number, we can write. How? This complex number equals its modulus within bracket cos its argument plus I sin its argument. That way we can write. Understand? Right? Then we can write therefore Z2 minus Z0 divided by Z1 minus Z0 complex number equals 1, its modulus, times cos its argument theta, cos theta plus I sin theta. Right? No? This is how we can write that complex number. Now you can use by this the cross multiplication to this end. Then Z2 minus Z0 is equal to Z1 minus Z0 times, right, cos theta plus I sin theta. Right? Right. Then people, at the new position P2, the complex number Z2 can be subjected by this. This gives us what? Z2 brings right hand side, Z0 plus Z1 minus Z0 times cos theta plus I sin theta. This is the people, the complex number represented by the point P2. This proof, people, in past papers you can see there are, I think, 1 or 2 papers in the past papers to prove this result. Okay. Right. This is the result. And without proving this result at the examination, you can straight away use. When you go through the question 2018 or 17, like that, in that years, this result had been used directly to get the answers. Right? But you have to remember this result, how to prove. The proof might be asking. Right? People, by using this theory, we can derive or deduce another 2 more results. Right. Now people, suppose this P0 P1 line segment is rotated about the point P0 in anticlockwise by an angle 90. Then theta becomes 90. Once you put theta becomes 90, theta 90, we are here in this result. We can obtain another new what result? Okay, yeah. All right. So then we can write next one, not. Right. We can take this one. Z2 minus Z0, this one I'm going to use, equals Z1 minus Z0 cos theta plus I sin theta. Right. Now, let theta equals pi by 2. Now, this P0 P1 line segment, P0 P1 line segment is rotated about the point P0 by an angle 90 in anticlockwise. Right. Then once you put pi by 2, we are here and here. Let's see what happens. Z1 minus Z0 on the right hand side, cos pi by 2 plus I sin pi by 2. You know, people, cos pi by 2 is 0, sin pi by 2 is 1. Then we get this z2 minus z0 is equal to, here we have I times this. Okay, this is what we get. People, now what is the result here we have? Then shall I draw this diagram for this result? When I draw this diagram, for the result this, what we get is this. Right. Now, P0, P1 is here. Line segment. This is Z1. This is Z0. Right. So now theta pi by 2, and we have rotated that in anti-clockwise sense. No, people, then this is the new position. This is 90. Here now we have, this is Z2, P2. P2 Z2 is this. Then P0, P1 line segment represents the complex number this. Right. Then P0, P2 represents the complex number this. And this represents Z1 minus Z0, right? This represents Z2 minus Z0. What? This line segment. People, then what can you understand by this result? Then Z1 minus Z0 complex number is multiplied by I. Right hand side, Z1 minus Z0 complex number is multiplied by I. After multiplying that by I, what has happened to that? That become this Z2 minus Z0. Where is this Z2 minus Z0? Z2 minus Z0 is this. That means this complex number is on the right hand side. We have, it is multiplied by I. Then once we multiply the Z1 minus Z0 complex number by I, that complex number rotates by an angle 90 in anti-clockwise sense. Then this gives us, when you multiply a complex number by I, that corresponding line segment rotates by an angle 90 in anti-clockwise. Understand? That's what this result says. Is it clear? Then people, about what point that line segment rotates? The point is, people, to the left and right, what is the common complex number available? About that point only, the line segment is rotated in anti-clockwise by an angle 90. Here, about the point P0 representing the complex number Z0 only, this line segment rotates, right, by an angle 90 in anti-clockwise. So that is the result. This result also very important result when you work out questions. What is the end result? When you multiply a complex number by I. People, you know, for every complex number, right, we can represent by polar form. When you represent like that by polar form, definitely for that complex number, there is a particular line segment. Right. When that complex number is multiplied by I, that corresponding line segment is rotated by 90-degree angle in anti-clockwise sense. Right? That's the result we get here. Okay. Come to this diagram, people. This is the imaginary axis. This is the real axis. This is already know. Right. Then we'll write. This result implies, when a complex number is multiplied by I, when a complex number is multiplied by I, the line segment which represents this complex number is rotated in anticlockwise sense by an angle 90 degrees. By an angle 90 degrees about the point from which the line segment begins. That's correct, no, people? This Z1 minus Z0 complex number, right? That complex number is represented by Z0, Z1 order. Here, P0, P1. Then P0, P1 line segment is the one representing Z1 minus Z0. Then the Z1 minus Z0 complex number is starting from people P0 point. Then Z1 minus Z0 is multiplied by I. That line segment, since it is starting from P0, about the point P0 only, that rotates in anticlockwise by an angle 90. Understand that, huh? Right? On the right hand side, about the second point, the second complex number we have now, about that point only the line segment rotates. To what sense? Anticlockwise. By what angle? 90. Okay, right. Okay, so then it is very easy. The arrowhead is going away from P0 now, then rotational point is P0. Right. Then people, when I put for this theta minus pi by 2, let's see what happens. Minus pi by 2 mean, people, this direction should be this way, clockwise. Then this P0, P1 rotates now clockwise by an angle 90. Let's see what is that result. Right. Number 2, note number 2, take. Note number 2. When theta, let theta, first write down this, let theta minus pi by 2. I rearrange this one, huh? Minus pi by 2. Then here we get cos minus pi by 2. And here minus pi by 2. People, sine minus pi by 2 is minus 1. Minus 1. Then cos minus pi by 2 is 0. Here minus I coming, therefore this is minus I. Right? Minus I. Here this is minus I. Now what is the result, people? Now what is the result? When a complex number is multiplied by minus I, the corresponding line segment is rotated clockwise sense by an angle 90. By an angle 90. This is the result. Right? Clockwise sense by an angle 90. We'll draw that diagram too. Initial position is this. Final position is this. P naught, Z naught. P1, Z1. P2, Z2. This way it rotates clockwise, right? Do I equal real axis? This is the axis. Origin now. Right. First do that diagram and we'll write in words. Right now. Then write down like this. This result implies when a complex number is multiplied by minus I, when a complex number is multiplied by minus I, the corresponding line segment is rotated by an angle (90°) in clockwise sense. Right. People, now third note is when this Z naught is 0. Z naught complex number is 0. 0 complex number is at the origin, people. When this Z naught is 0, then the rotational situation takes place about the point O. Right. Then you can write number 3, the node number 3. Then you can write note number 3. When Z naught equals 0. When Z naught equals 0. And theta equals pi by 2. Then the complex number, the line segment which represents the complex number Z1, rotates about the point O, about origin, rotates about origin O. Rotates about origin O. In anticlockwise sense. People, this is Z1. Then this complex number is IZ1. rotating anticlockwise. When you multiply this by I, right? This complex number is Z1, theta pi by 2, Z naught 0, no? Then rotational point is origin, right? So then when theta is pi by 2, we said anticlockwise sense, it rotates. Then when you put here people, in the earlier case, we had something like this, no? Z2 minus Z0 is equal to I times Z1 minus Z0, no? If this is 0, to the left-hand side, we get Z2, right-hand side, Z1. Then the new position complex number is Z2, it is equal to IZ1. IZ1. Right? So therefore, if the Z1 is this, IZ1 is people rotating that line segment representing Z1 by an angle 90 anticlockwise. The new position comes. Right. Next one. Next one, write down. Fourth one. When Z0 equals 0 and theta minus pi by 2, then what can you say, people? The complex number which represents the line segment which represents the complex number Z1 is this. This is Z1. Rotates clockwise sense this way. Then this line segment represent minus IZ1. This way it rotates, huh? It is anticlockwise. Real axis, imaginary axis. Right. Right, people. Now we come to one question. Right. Let Z1 or Z be a complex number then represent two IZ and minus root 3 IZ complex numbers in the Argand plane. In the Argand plane. Right. Well, now suppose you see we have a complex number in the polar form like this. Z equal to 2 times cos pi by 4 plus I sin pi by 4, for example. How do you draw this complex number? The length of the line segment should be 2. Starting from origin, length is 2, making pi by 4 angle with the real axis like this. This is 2 units. This is a point which represents the complex number Z. Right. You then tell me how to represent 2Z. 2Z. To get the 2Z, we have to multiply both sides by 2. Then 2 into 2, this cos pi by 4, right, plus I sin pi by 4. Since we multiply by positive value, this argument won't change. Here 4. Cos pi by 4 plus I sin pi by 4. Then people, to represent the 2Z complex number, what you need to do is, people, on the same line, right, this length of the line should be doubled. We have to produce this line from here, the same length. Then its ending point only, the 2Z available. And then we can write 2Z complex number, this and this being equal. This is the point. People now say Q representing 2Z complex number. Now, before answering these, people, if you need, you can just put this in a note. Let us say this 2Z we can write like this. Then you can very clearly understand how to mark this 2IZ then minus root 3IZ. Right now, people, this thing you would understand very well now, right? Now we'll come to this. This is the Argand plane. Axis, major axis. Let this be the complex number Z. The corresponding line segment is this. Right. Now I am going to first mark 2IZ. Right. People, I can think the 2IZ complex number like this. 2IZ complex number I can consider 2 times IZ. Right. First, I am going to represent this IZ complex number. IZ complex number means multiplying Z complex number by I. That means this line segment you have to rotate by an angle 90 in anticlockwise about the point O, because the complex number is starting, the line segment is starting from origin. No? Then about the origin only we have to rotate. Then rotate it in anticlockwise sense by an angle 90. Then we get this. That should be multiplied by 2. Then people, that length we have to double it. Then at the ending point we have 2IZ. Okay, all right. So then first rotate this way by an angle 90 in anticlockwise sense, because we have multiplied by I now. Anticlockwise. Right. This length, if we take this way, this is 90. This is the point which represents 2IZ. Right now, rotate the OP line segment by an angle 90 in anticlockwise sense and double it length. This length and this length being equal to 1 this. Right now, first part is that. Second one, people. Minus root 3IZ. This one I can write root 3 minus IZ. Root 3 minus IZ. Z complex number should be multiplied by minus I. When you multiply a complex number by minus I, that complex number, the line segment that represents the complex number rotated clockwise by an angle 90, right? Then this position. This here. Here it is rotated this sense, this is rotated in this sense. Until what? Until the crescent length should be extended √3 times. √3 times, right? Let this be, people, point Q. Right. Point Q represents what? Minus √3 IZ, right? This way. Use this way like this. Then OQ length is such that √3 times OP. This is how this point Q lies, and then this is the point. Right, people? Yeah. This is how we represent those points on the Argand diagram. Right. This is a very important theory, people. Right. Any question here?